Hello friends, did you know that there is a mind-blowing new theory that the universe began with a spectacular firework and a fire show? Scientists call this new theory Pop III.1 model. And this new concept suggests that the very first stars exploded in a brilliant flash of light, creating all the supermassive black holes that we see today, and also in the process illuminating the cosmos. Let's go. Welcome, stargazers, to this exploration of the cosmos like you have never imagined. For centuries, we have gazed up at the night sky, marveling at the vastness and the intricate dance of galaxies. But what if I told you that universe began not with a quiet hum, but with a dazzling explosive spectacle, a cosmic firework, and a show of unimaginable scale? Today we are diving into this fascinating new theory that suggests the supermassive black holes and those enigmatic giants lurking at the heart of galaxies were born from the universe's very first stars in a breathtaking flash of light. This dramatic idea, often called the Pop III.1 model, and this could revolutionize our understanding of the early universe, explaining how these colossal stellar remnants grew so incredibly large so quickly after the Big Bang. So friends, get ready to have your cosmic perspective shifted little bit only. To truly appreciate the firework theory, we need to journey back in time to the very beginning. Our current understanding is that the Big Bang theory describes the universe was accumulated at a very small point, originating from an incredibly hot, dense state around 13.8 billion years ago. And in the initial moment, the universe expanded and cooled rapidly. Eventually, after about 380,000 years, the first atoms, mostly hydrogen and helium, were formed. This era is known as the recombination epoch. The afterglow of this epoch is still detectable today as cosmic microwave background radiation, a faint whisper from the early universe. But what happened next? The period between the recombination and the formation of the first luminous object is known as, we call it, dark ages in the cosmic proportions. It was time when the universe was filled with neutral gas waiting for a spark that could ignite the cosmic dawn. Then came the first stars, population 3 stars. These weren't like the stars we see today, formed from the pristine gas devoid of heavier element, which we call metals. They were likely massive, hot, and short-lived. Scientists believe there are two main types, which is Pop III.2 and the smaller and existing in clusters, and the rarer type, which is gigantic Pop III.1 stars. Now there is where our firework show begins. The Pop III.1 model proposes that some of the first colossal stars did not end their life in typical supernova. Instead, due to their immense mass, their cores may have directly collapsed into a black hole. And not just any black hole, but seed black hole that were already quite substantial. But the firework aspect comes from what happened during the collapse. The theory suggests that these giant stars died and they unleashed a spectacular burst of high energy radiation, a flash of light so intense it ionized all the surrounding neutral hydrogen during the early universe. Imagine the entire cosmos being briefly illuminated in a grand, fleeting display. This firework and the fire show wasn't just visually stunning. Well, if anyone was around to see it, this intense ionization played a crucial role in shaping the universe we see today. It marked the end of cosmic dark ages and paved the way for the formation of the first galaxies and the subsequent generation of stars. This era of reionization is a key period in cosmic history, and Pop 3.1 model offers a compelling explanation for how it occurred so rapidly. But the implication didn't stop there. One of the biggest puzzles in modern astronomy is how the supermassive black holes, millions or even billions of times the mass of our sun, could have grown so large so early in the universe. These behemoths are found at the centers of almost all large galaxies, and their existence in early universe challenges traditional black hole formation and growth models. The Pop 3.1 model offers a potential solution by starting with relatively large seed black hole formed from the direct collapse of massive first stars. These black holes had a head start in the cosmic growth race. The subsequent accretion of the matter, gas, and other stars falling into their gravitational pull could then lead to supermassive black holes that we observe today. Furthermore, this firework theory might even shed light on another major mystery, which is known as the Hubble Tension. This refers to the discrepancy in the measured rate of universe's expansion depending on whether we look at nearby objects or cosmic microwave background. While the Pop 3.1 model doesn't directly solve the Hubble tension, some variations suggest that the energetic output of these first stars could have subtly influenced the early universe expansion rate in ways we are only beginning to understand. And finally, the Pop 3.1 model directly addresses the nature of cosmic dawn, the period when the first luminous sources in the universe turn on. The intense burst of radiation from the collapsing Pop 3.1 stars could have been a significant contributor to this epoch, ionizing the intergalactic medium and allowing light to travel freely through cosmos. Now, it is important to remember that the Pop 3.1 model is still relatively new and evolving theory. Scientists are working hard to find observational evidence to support this whole theory or refute it. This involves searching for the faint remnant of these first stars or the unique signature they might have left in the intergalactical gas. Telescopes like James Webb Space Telescopes are playing a crucial role in this quest, peering deeper into the early universe than ever before. One of the challenges in confirming Pop 3.1 model is the rarity of these massive first stars. They were likely few and far between, and their short lifespan means they are long gone. However, the black holes they left behind or the impact of their intense radiation could still be detectable through careful observations. Scientists are also exploring alternative theories for the formation of supermassive black holes, such as the direct collapse of large clouds of gas without forming the first stars. The future observations and more sophisticated simulations will be crucial in determining which model best explains the universe as we observe it today. Regardless of the ultimate answer, the